Okay, so we are still looking at section 5.5. We're on example 2, and we are looking at, this is on indeterminate torque. And so because we have torque, we have shear stress, which is TC over J for maximum, and we have that angle of twist, which is TL over JG. Okay, so we have a steel shaft which has a diameter of 60 millimeters. It is fixed at both ends A and B. It is subjected to the torques shown. Determine the absolute maximum shear stress in the shaft. So I need to know the reactions at A and B so that I can do my little free body diagrams, and I can cut and find internal and cut and find internal and cut and find internal, so we can figure out the torques that are in each section. So we've got to have those reactions. So the first thing I always start with is equilibrium. And when I look at equilibrium, I'm going to draw my shaft here, and we have 500 Newton meters, 200 Newton meters. I'm just going to do it that way. Torque at B, torque at A. So if I sum torques equals 0, I'm going to get that torque A plus torque B equals 700 Newton meters. Okay, so that's my equilibrium. And when I set up my equilibrium, it's very easy to see that I have one equation and two unknowns. So now I have to do the second part, which is deformation. And the first problem that we did in this section, we looked at that compatibility of that phi equals phi. This time we're going to use the force method, which is where we remove the redundant, allow rotation to take place, put the redundant back on. So let's look at the deformation. And we're going to use that force method, because we're going to have to force it back into place. Okay, so the first thing I'm going to do is remove redundant. Okay, so if I took this off, it would still stick in the air, right? It behaves differently once I add A back on. So let's just remove A, and then we've just got this one unknown B. But if I remove A, it's going to allow that shaft to rotate. So I've got 500 Newton meters. I have 200 Newton meters. And back here at B, I'm just going to assume it's going in that direction. So I have a torque at B. I have 1 meter, 1.5 meters, and 1 meter. So now I have to figure out, well, what kind of twist are we having? If this is free to rotate now, I can see that I'm actually going to get a phi that comes from the torques that are applied. Okay, and so we're going to have to sum up the phi that, is from B to D plus phi from C to D, okay, plus phi from A to C. So as we're twisting this, it's because we're applying these torques here, and then here it's going to change the amount of torque we have in each segment. So let's start here at A. So we have A, C, D, and B. So if I look at A, and I take my Post-it note, my handy dandy Post-it note, and we work our way backwards. I'm working away. I can see that there's no applied torque. So if I have no applied torque, then if I'm looking at the torque from A to C and I sum those torques equals 0, the torque from A to C equals 0. So it's going to be rotating here at the end because we have torques in these other segments that are rotating. It's just kind of like going along for the ride. Now we're going to move back again. And I have 500 Newton meters. And so internally, I'm going to assume positive rotation, torque from C to D, and I'm going to sum those torques equals 0, and I'm going to find that torque from C to D equals negative 500 Newton meters. Perfect. I can now determine the angle of twist in here. The length of this length is 1.5. That's what I'm cutting, is that length. Now I'm going to go back here, cut, and we can see we have 500 Newton meters. We have 200 Newton meters. And so if I make my cut, I'm going to assume positive going this way. Actually, coming from the left, it's coming towards us is positive. Coming towards us is positive. Then when I sum those torques up, that's from D to B, I'm going to get that torque from D to B equals negative 700 Newton meters. Okay, so now if I want to know the rotation that's occurring, I'm going to have the rotation from the torque equals, well, I know that rotation, not theta, rotation is TL over JG, so I can look at my first segment. We have 0 rotation because there's no internal torque. Then we're going to have plus, okay, plus negative 500 Newton meters, and its length of shaft is 1.5 meters, divided by JG, plus, and then I have negative 700 Newton meters, times its length of shaft is 1 meter, divided by JG. And so that's the rotation that I end up getting from the applied torque. So now we're going to put redundant back on. So if I take that same shaft, and I have my little reaction there at B, and I've been twisting this way, so let's apply a torque at A, and we can see that it is going to have, as this is twisting towards us, this has to be twisting us back into place. And because I remove all of these other forces, it doesn't matter where I cut it. It doesn't matter where I cut it. That internal, so here's my torque A that I've put on. I'm going to assume it's positive. So here's my internal torque in that the whole system from A to B. So now if I sum my torques equals 0, I'm going to find that that internal torque equals the torque at A. And so the whole thing is rotating, and because it's the same diameter and the same material, we can just look at the entire length of 3.5 meters. If we had different materials, we'd also have to cut it and cut it and cut it, but it would still be that same torque at A that's causing that internal rotation. So the internal torque equals that torque at A that's putting it back into place. So when I look at the rotation of that torque at A, it's going to equal, well, the internal is torque A, the entire length is 3.5 meters, and J and G. So we now have this relationship that if I allow twisting to take place, I'm going to get a value. Okay? As I put this redundant back on and force it back into place, this is what's going to have to happen. So I know then that, okay, so now let's look at our compatibility. I know then that phi from the applied torques plus phi of the torque at A has to equal 0 because it's going back to its original place. So I can come over here and I've got negative 500 times 1.5 divided by JG plus negative 700 times 1 divided by JG plus the torque at A times 3.5 divided by JG, and all of that equals 0. Okay, all of that equals 0. Well, the beauty of this being the same material and the same diameter is that these are constant. We can multiply through and get rid of them. And I now have negative 500 times 1.5 minus 700 plus 3.5 TA equals 0. So TA equals 500 times 1.5 plus 700 divided by 3.5. So the torque at A, and one of the reasons I like this method is because then I don't have to have 2 equations and 2 unknowns, which is what happens if we do the compatibility of deformations. We end up with unknown TA and TB, and that's just a lot more work. So we have 500 enter, 1.5 times 700 plus 3.5 divided by, and I get 414.3. And my units are going to be Newton meters. So if torque A is 414.3, I can go back to equilibrium. And we can see then that torque A, 414.3 Newton meters, plus torque B equals 700 Newton meters. So torque B has to equal, find 700 plus 285.7, 285.7 Newton meters. So now I need to draw my torque diagram because it says determine the absolute maximum shear stress. So I have to determine, does the maximum occur here or in this part or in this part? And this is easier because again, it's all one material, all one geometry. Then I just need to figure out which internal section has the largest internal torque, and that's the section that will have the largest shear stress. Now, if these had different geometries, then knowing that it's TC over J, I would have to calculate at where I also had a different geometry. So let's figure out now our internal torques. And how do I figure out our internal torques? Well, we make little cuts. So I'm going to start here all the way at the left, and I know that torque A, so I'm going to make a cut here and then here and then here. So I'm starting at A, and I have a torque at A of 414.3, 414.3 Newton meters. And that means I'm going to assume positive on the inside coming towards me. So this is the torque from A to C. Well, I can see they're equal and opposite. So torque AC is indeed a positive 414.3 Newton meters. And then I'm going to come along with my little post-it note. There's my next picture. So I'm going to come along like this. And I have 414 Newton meters. And I have 500 coming back towards me, Newton meters, and I'm going to assume it positive, torque CD, and then I'm going to sum those torques equals 0, and I'm going to say coming towards me is positive, so I have negative 414 plus 500 plus torque CD equals 0. And so I can quickly see that torque CD equals negative 500 plus 414. So I want to move that over, negative, it's going to be a negative value. So I assumed it positive, got a negative, so now I know it's negative. So that torque CD, that torque CD equals negative 86 Newton meters, okay? And now I need to determine what's happening from D to B. Well, I'm going to go backwards this time. And I'm going to look at D to B. So I've got this little picture like this. I know that B is going backwards, and B was equal to 285.7. And butt of my hand goes to the butt here, so we're going to assume positive torque from D to B. And when I do my summing of my torques equals 0, I'm going to look, they're both going the same direction, so I assumed it positive, but it has to be negative. Okay, so I've now determined my torques, and now I'm going to draw a torque diagram. I'm really trying hard to get this all on the same page. So I have my shaft that looks like this, and I have 500 Newton meters coming this way. I have 200 Newton meters coming this way. I have my reactions at the wall are going to be 414.3 Newton meters and 285.7 Newton meters. And so now I can just kind of draw down like so. And we calculated that internal torque, which is in units of Newton meters. And I got from A to B was a positive 414, positive 414.83. And then from B to C, I had negative 86. And then from D to B, I had negative 285.7, negative. So if I'm looking then at my shear stress, the absolute positive magnitude is going to be where I have my maximum torque, which is 414.83 Newton meters. So my shear stress is going to be 414.83 Newton meters. Is that what that value? Oh, I don't know where I got 83 from. It's just a 3. I just like to make up extra stuff clearly. 414.3. 414.3 Newton meters. 414.3 Newton meters. And C comes from the radius. It was a diameter of 60 millimeters, so my radius is 30 millimeters, which is 0.03 meters, divided by its solid pi over 2.03 meters to the fourth. So that maximum shear stress is going to be 414.03 times pi as a number to divided by 0.03 enter to the fourth times divided by a large number. 1, 2, 3, 4, 5, 6. 9.77 Newton meter squared, which is a Pascal, but we also moved over 1, 2, 3, 4, 5, 6. So it's times 10 to the 6th Newton per meter squared. So our maximum shear stress is 9.77 megapascals. So there's that shear stress. Now again, if we'd had different sized diameters here, like if this had gotten a lot smaller, then we would have to go back and actually check the shear stress at each of these places because it's going to get a different shear stress if we have different values in here. But because it's all the same diameter, we can go with the largest shear stress or shear force torque to get the shear stress. We could also then draw a shear stress diagram, because why not? And this is going to be shear stress in megapascals. And I would have 9.77. And I know that the shear stress here, they would all be negative. They would be less than that. So positive, negative, negative. And there we have it. So that's our final answer.